Okay, so recording is started. Hello, everybody. We are here to this technical presentation offered by Dr. Ryan Evans for the Toronto STLE section. I'm going through Dr. Evans' bio, and then we will pass the mic to him to go through his presentation. Dr. Ryan Evans is the Director of R&D at the Timken Company, where he is the global lead for research and development activities, including the identification and development of new product, materials, and manufacturing technologies to meet customer needs. He joined Timken more than 20 years ago as a researcher in the field of advanced materials and made significant contribution in the areas of thin film coating, lubrication, advanced material characterization, and tribology. He has more than 60 technical publications and 14 patents in these fields. He earned a Ph.D. in chemical engineering from Case Western Reserve University and is a fellow of ASM International. He has participated in STLE since 2002, including volunteering as a member of the award committee, annual meeting program committee, rolling element bearing technical committee, and surface engineering technical committee. He is currently serving a one-year term as 2022-2023 STLE president. Dr. Evans, please go ahead.
Okay, thank you, Beshad. I appreciate the introduction, and it really is a pleasure to speak with the Toronto group. We've had a pretty exciting year with STLE to this point, and STLE we regard our fiscal years from July to June 30th. So that allows us to kind of use the annual meeting as the kind of crowning moment of each year. And so really since our last annual meeting in Orlando, we've been working on a lot of really great things. So what I want to do is start by just introducing the company that I work for and have worked for, Timken. I'll then talk a little about some of that stuff with STLE that I was just mentioning that's top of our list at the moment. And then I'll get into some technical discussion around what Timken does, and that's engineered bearings and industrial motion components. Timken is predominantly a hardware company, so we don't make base oils or formulate lubricants per se, but we rely on fluids and lubricants certainly for our products to succeed in their application purpose. So I'll talk about some of the trends we're seeing in engineered bearings around battery electric vehicles in particular, some more modern work we're doing with lubricant rheology and bearing power loss prediction, with sustainability being a concern and really top of mind for most people and companies lately. Minimizing the friction in lubricated bearings is critical, and so we're trying to push the state of the art on that front. And then tribological coatings are another means by which you can prolong the wear life of bearings. And so I'll do a brief few comments on that. And then I'll get into the non-bearing stuff, industrial motion components, and really kind of align some of the topics around trends we're seeing in robotics and automation expansion in industry, automated lubrication systems to support all types of production equipment and vehicles, for example, but also strain wave gear drives, cycloidal reduction gearing, and linear motion bearings for robotics applications in particular. So these have integrated bearings of certain types, but require different lubrication needs have different lubrication needs than just a standard rolling element bearing, for example. So the Timken company, these are 21 numbers, just timing here. We're going to be updating this for 22 as we announce to the street here in a few weeks. But the company was founded in 1899. So think about pre-automobiles in the USA, at least. We were founded by a guy named Henry Timken, who was a German immigrant to the US that had an axle company, so for freight wagons in particular. And what he found was that plain bearings for axles for freight wagons wore out, especially when you turn corners, due to thrust loads that weren't accommodated properly with just standard sleeve bearings. And so he designed a rolling element bearing that could accommodate both radial and axial load. He didn't invent tapered roller bearings per se, but he innovated tapered roller bearings that worked well in his end use. So he was really kind of an end user that developed a component to meet his needs. And the company launched from there. I'm based in North Canton, Ohio, which is northeast, just south of Cleveland, about 60 miles in the Canton Akron area. And the company was founded here because of, at the turn of the century there into the 20th century, there were um, huge activities in automotive as the automotive industry was launching in Detroit, but also the steel production through from Chicago through Cleveland through Pittsburgh and that whole Rust Belt area. The company has more than 18,000 employees worldwide in 42 countries. We do pay dividends, and revenue in 21 was about 4 billion. I think you'll all see a bigger number for 22 when we announce. I'm sorry, 21 was 4 billion, 22 is to be announced. Product offering, the pie chart there, mostly about 2/3 engineered bearings, 1/3 mechanical power transmission products, or what we're calling industrial motion products now, with a decent split between OEM and distribution or aftermarket type customers. About half of what we do is in Canada and the US, and the other half elsewhere in the world. So pretty North American centric company there, at least. Originally, we are expanding globally, though, of course. As I just said, engineered bearings, rolling elements, and plain bearings. We recently acquired a company called GGB from Enpro, and they have a full line of metal polymer and other plain bearings that they offer. So we've just broadened beyond rolling bearings into plain bearings as well. And our industrial motion products are machine components of all types, from couplings to chain to belts to gear drive units to different repair services and so on. I'll go right to STLE now. This is the current board of directors. So that's me sitting there beside Ken Hope, who's immediate past president. Professor Hong Liang from Texas A&M is the current vice president, so she'll take over the presidency in May. Jack McKenna from Sealand and Kevin Delaney there from Vanderbilt, secretary and treasurer, with Ed Salig, the executive director, sitting there as well. And you may see some other folks in here that you recognize as well on the board, including Khalid there. And so we have a pretty good board, a diverse mix of industry and academia, and are working on a lot of exciting things right now. STLE works to a strategic plan. Our current plan expires here this coming May in 23. This one was set out in 2020. So I've been around long enough to have had a hand in the 2020 plan, and then we'll certainly drive the 23 to 26 plan that we're working on now. But just at the highest level, the purpose is to enhance our mission, maintain industry relevance, and really this connect, learn, achieve. It all starts with the community of professionals that we are in our field, and STLE wants to facilitate connection amongst members of that community, learning opportunities, and then achievement, whether it be through volunteer service or through publications, papers, awards, and so on. Our mission is to advance the science of tribology and lubrication engineering, with the end goal of fostering innovation around performance of equipment products, always with an eye on conserving resources and protecting the environment. If you go back to the Jost report, where the term tribology was coined in the UK in the 1960s, there was an eye at conserving resources and protecting the environment and really trying to minimize wasted energy in the UK economy. STLE really considers that to remain part of our mission. And then the vision is perfecting motion. So I wrote a president's column in TLT about that several months ago. But perfecting being something that's ongoing, never really reached. But motion, there's no tribology or need for lubrication without motion. And so, by our tribological technologies and practices and solutions and talent, we have a real good shot at optimizing and perfecting motion as well as we can in our roles in the companies and universities and community we serve. Taking it down just one more layer, there are 4 different domains that we consider around this vision that are part of the strategic plan. What's not shown here are tactics. So we do have a list of 5 to 10 bullet tactics under each of these domains, but it's already wordy enough, so we didn't put those in just the summary slides. But just so you're aware, the strategic domains we're focused on are around education and professional development. There is no profession in the future without training new talent, um, from young people to mid-career to late career folks that need to join our field. We want to provide the types of materials and training and standard know-how that can be disseminated through to our new members. The domain number 2 is technology and innovation. So STLE is focused on tribology, and I think there's a bit of a misnomer around our field that it's a mature field. Certainly, it is mature. There are mature tribology technologies. There are mature lubricant technologies, but there's also a lot of cutting edge innovation and an awful lot of unknowns that are out there that we are still striving to wrap our minds around and contribute to the world by working through and figuring out. So with sustainability and some of these other resource related challenges for the world at large, we do see tribology and lubrication technology playing an important role in driving forward mankind's progress on those fronts. Communications and advocacy is around promoting the profession. You're not going to have people interested in the profession without some type of access to what it is we care about, what it is we do, and some of the contributions we're making to our field. And so our ability to communicate what it is we do and advocate for our interests as a group is important. And then lastly, organizational efficiency. So this is maintaining that full-time paid staff. I'm a volunteer leader. I don't take anything from STLE at all. It's pure, my company's sponsoring my participation here. That's true for the executive council, the board of directors, and so on. But Ed Salik's organization, they are full-time paid staff, and like running any business or any type of organized group, you need to have strong organizational efficiency. So there are some tactics there strategically to improve the staff and the type of resources that the staff makes available to the local sections and the membership as a whole. Won't spend too much time on this, but just looking, I always like to look back one year and then into the current year. We did our first EV conference in November of 21, 334 attendees. This white paper was published. We launched a podcast. We had a successful Orlando annual meeting. The 1,300 attendees is solid, average to better than average in terms of historical attendance. If you're thinking about top ever kind of attendance, it's in the 15 to 1,600 range. Low end is like 1,000-ish. The 1,300 is right in the kind of average sweet spot. So coming back after 2 canceled on in-person annual meetings in Orlando worked out pretty well overall. We did create a mechanism now by which people can donate to our scholarship committee, or not our committee, but to our scholarship programs. Prior to this point, we paid for scholarships each year out of our operating budget for the staff and the society. Um, that made donating for specifically for scholarships kind of nebulous to people and not very desirable. With the creation of this new fund and then the front end funds that are supporting that, or kind of the face of this fund to the rest of us, we have now the ability to donate funds in memory of someone, maybe a member who passed away, a mechanism now for donations from um, estates, uh, corporations that want to donate to scholarships, and so on. I mean, even individuals. If I want to write a check for $100, I can donate that. There'll be more to come on how to do that and how to make all that work upcoming, but rest assured that every penny going into this is going directly to students and other scholarship programs, investments for the future, rather than just our normal operating budget, for example. We were able to weather the storm of the pandemic with insurance policy payments and government pandemic support. So we're very financially sound. And then, yeah, section rebate revision, a minor change there to increase that, and then launched Industry Insight online discussion groups. In 22-23, so where we are now, so from last May to this coming May, we not just planned, this is a month or so old slide, we just had our second EV conference at Southwest Research Institute. We are working on a next emerging trends report. Rather than polling our membership for people's opinions, we're actually interviewing subject matter experts. And so it'll be a different vision of that, a different embodiment of that emerging trends report. The TFC was postponed to 23. This was a cascaded postponement from the pandemic. And so what we're doing is actually combining the third EV conference with the TFC in Cleveland this coming fall. And so it'll bring together the mostly academic TFC crowd with the mostly industry focused EV crowd in a single location in the fall. And we're really excited about what co-locating those two meetings can look like. The annual meeting is planned for May in Long Beach, California. I'm sorry I don't have the graphics and things in this list, but it's certainly on STLE.org. You can check that out. Again, the exhibition sales, the technical program, everything has been lined up very well. It looks to be, again, kind of an Orlando scale, if not larger meeting, just based on where we stand at the moment. So we're really excited about going out to the West Coast for the first time in a while. I'm an Eastern guy, so it's more travel for me, but it will be hopefully a nice event. A couple other topics: diversity, equity, and inclusion. We did an ad hoc committee on that under Ken Hope's presidency. Now we have governance working on a committee charter for a standing committee for a DEI group to advise the board on DEI opportunities. It is still STLE's mission and part of our mission to be as inclusive and diverse, welcoming as many ideas, contributions, and leadership from people in our field, regardless of their other kind of identifying or regardless of how they identify within the world at large. And so we want to be as accommodating and so on as possible there. So I'm expecting we will have a DEI committee approved by the board here later this month, and then we'll move forward with some of that opportunity as well. Certification program reviews are underway. Digital test taking, some of the other things are there. Rebecca Lintow from staff has the head of that. And then this other bullet down here about LMS, it's an digital education offering system. Very kind of modern video-based kind of training platform that Rebecca's working on here with volunteers, of course, and uh, with an eye towards that education domain in particular. Scholarship committee, SIF fundraising strategies. Like I said, there'll be more to show on that here in upcoming meetings and communications. We did have a bit of a dip in membership. Um, so there's a special initiative going on this year to try to re-energize those counts. That is going well. In fact, our numbers have taken off pretty well this year. So we're excited about that. And then lastly, staff succession planning and backfills remain something we need to keep an eye on as well. Gene just resigned um, because not for any issues with the staff or STLE, but just family kind of timing. And so we are looking to backfill that position on the staff as well. Okay, so let me get into some technical stuff here. Maybe we can pause it. If anyone has any questions on the STLE administrative piece of this, we can do it now if you'd like, because I'm going to shift directions.
Well, I don't see any question in the chat, so
Okay, cool.
somebody has a
So
question. Yeah.
yeah, if you have them, we'll hit them at the end. I'm just going to keep going here. I want to talk first about engineered bearings. So for people that aren't bearing experts, I have the kind of oldish cartoons here showing ball bearings. So you have balls separating two rings, that can rotate relative to each other. Spherical roller bearings aren't ball bearings. They're kind of barrel-shaped rollers, like you can see. And the reason they're called spherical is that the outer ring has a spherical profile. So you could actually that's just a constant radius. So you could put a ball in there if you wanted to. But what that allows you to do is tilt and misalign the inner ring relative to the outer ring because of the constant radius kind of outer shape of the spherical bearing. Cylindrical roller bearings are just cylinder shaped rollers between two rings, and then tapered, as I was talking about earlier, have a truncated cone. So it's like a spherical roller, but with one end diameter larger than the other. And to accommodate that, you need to have a guide flange on the inner ring usually, and then an outer ring we call a cup. So the reason you have multiple types of roller bearings is because of application loading and speed considerations. Ball bearings, can take kind of medium to low radial load. So think about like if this is an axle bearing the weight of the vehicle, and kind of smallish thrust load because you do have some curvature to the raceway that can accommodate that thrust load. But if you look at a cylindrical roller bearing, you could take big load, radial load, because you have line contact, which distributes the pressure, distributes the force across a larger area of contact. But again, very low thrust load capability because you don't have any kind of constraining geometrical feature there in that outer ring to hold it. This is just one design. There are several types of CRB, of course. SRB, big thrust or big radial load because of the line contact, higher thrust load capability, again, because of the curvature of the raceways. And then tapereds can do big thrust and big radial load. The trade-off is in speed. So when you have line contact, anything you can handle high load generally has lower speed limits because you have more contact area and therefore more friction that could generate heat versus balls where you have like a point. So the ball's touching the raceway in a point in a standard deep groove ball bearing, for example. A little more on tapered bearings since Timken made our name in tapered bearings originally. You can do multi-rows. You usually have the ability to do axial adjustment. So if I move this cup mounted in the housing just ever so slightly, to the left of where it is now, I can control the load zone of what rollers are touching the cup and cone, and therefore the torque or the energy loss of the bearing. There's usually an optimal axial adjustment or setting, we say, but you can play around with that based on your application needs. And so, like I said, the adjustable setting here, by adjusting the axial internal clearance, I can adjust the load zone, and so how my load is distributed, and then the accompanying frictional losses of the product as well. I want to get into, where some of these bearings are used in electric vehicles. Everyone's talking electric vehicles, and so I will do the same. Um, when you think about battery electric vehicles, in the simplest designs, you have usually a low mounted battery pack, which adds a lot of weight. Um, and you need to support that weight with your two axles overall. And what that requires is a higher gross axle weight rating. So I now have a heavier vehicle due to my battery pack, at least today. I need to have bearings that can accommodate that at my wheel end. So wheel end bearing is the bearing that allows the wheel to rotate relative to the car itself. Um, Earliest battery electric vehicles have poor energy density compared to gasoline, and so that's where the weight comes from. But we do see a future where they go to solid state batteries, the battery packs lighten up as the energy density increases and so on. So you say, all right, I take out the gasoline engine, the transmission, and I go from a battery to motors and like say e-axles or small gearboxes to take the high-speed motor output to the wheels themselves. The fact that the battery pack's placed low in the chassis does change the center of gravity, so that affects the wheel end bearing designs as well. And we do see that a lot of EV projects, I will say that most of the research and development we're doing around bearings these days, at least especially in automotive, is in electric vehicle designs. Almost all of them. I mean, we're not doing any um, internal combustion engine kind of projects really at all at this time in the R&D mode. Um, but there is still that desire to use existing components in the chassis, suspension, and so on. And so the OEs are trying to go to the simpler design, but use bearings that are as similar to what they're used to as possible. So, anytime you're designing a bearing, this is an example bearing here where you would have your rotor bolted on to these studs, and then you bolt this into your frame. This is your little anti-lock brake sensor that reads called a tone wheel in between the two tapered bearing rows. This is all sealed and greased normally. Um, because you have higher weight requirements for electric vehicles, you need to generally increase the life of the life prediction for your design. So you're going to have to usually upsize it if you're using ball bearings, or in this drawing you have a tapered bearing. Um, Most of your wheel end bearings today in light vehicles are ball bearings. The exception to that will be like light trucks, like a Ford F-150 is going to have a front end bearings are going to have double row tapers like this is showing. Um, but when you go to electric versions of these, we're actually seeing some ball bearing wheel ends convert to tapered bearings because of the higher load requirements. You do have larger spline specs just due to the torque, the low end torque in electric motors. So we have to redesign the way the axle engages the bearing itself. And then, with the weight and the center of gravity, there's stiffness implications, there's efficiency implications. You want to minimize the amount of size and weight of the product of the wheel ends, but with power loss being a critical design characteristic that you need to optimize. And then standardized parts, which is kind of normal. So this is just comparing, like if I have a wheel end where I have an internal combustion engineering engine ball bearing, versus a ball bearing for a battery electric vehicle for the same general, say, pickup truck, versus a battery electric vehicle tapered bearing. This is where you get into that comparison, like I was saying earlier, where if I want to keep I want to keep the wheel end bearing the same size, the best way to do that is by going to a tapered bearing um, versus going to a larger ball bearing. And the reason for that is that you can see the capacity predictions here, the standard dynamic capacity of 1. You can actually get more capacity in the same size out of the tapered. You would have to upsize the ball bearing to, you see the much, about almost 2 millimeters, millimeter and a half larger ball diameter to get to the same dynamic capacity there as the internal combustion engine version. And then you start comparing other dimensions, cup pilot OD, hub flange OD, IDs, and so on. We can match the dimensions pretty evenly with the tapered bearing with even capacity to spare versus the ball bearing. Now the trade-off there is going to be in the efficiency of the bearing. I can handle more load, but as I said earlier, tapered bearings generally have more friction than ball bearings because of the line contacts. So what's good for load carrying isn't great for friction in a general sense. But with modern lubricants and other types of low friction technologies, we're getting closer and closer to that. So anyway, just a comparison to show you kind of the wheel end thinking that goes into bearing design with some of these considerations. The lubricant selection, we're talking greased bearings at the wheel ends. If you're taking higher load, you need often a different grease for a tapered wheel end bearing versus a ball bearing. Higher load carrying capability, sometimes higher viscosities, non-standard additives, antioxidants, and some of the designs we're looking at, there's a independent wheel end motor right at the wheel. So in the previous kind of example, that's an electric axle where you're driving an axle and then you're putting that axle through the bearing, turning the wheels. This is where you have the four independent wheel end motors. You have the motor smashed right up against the kind of the final drive, usually a planetary, right by the bearing, and the heat from the motor can soak into the bearing itself. So the higher temperatures are real, and depending on the type of design you're using, and that can have significant lubricant implications. Going to the electric axle, so I was just talking about wheel ends, so the bearing that makes the wheels turn or allows the wheels to turn. The electric axle takes the rotation out of the motor and distributes that to the axle. The analogy there is like a conventional hypoid gear differential in an internal combustion engine vehicle, where there you'll have hypoid, you'll have like 5,000 RPM kind of top speed in your bearing and in some of these rotating joints, 75 W80, 85 type gear fluids, splash lubes. So you just put it in your axle center and it splashes around there. The housing's kind of designed to encourage that. Operating temperatures in the 60 to 100 centigrade kind of range, cast iron, and so on. In some of these e-axles, though, you have kind of a parallel shaft situation where you have the motor coming in and you have driving a couple parallel shafts to a differential, which then go out to the axles. So helical gears instead of hypoids, much higher speeds, 10 to 20,000 RPM, ATF kind of lubricants, and viscosity grades, which could be challenging as well. Splash. There are some kind of dry e-axles that have grease lube bearings, so they're sealed and greased. Operating temperatures can be higher again because you're closer to that electric motor. Aluminum housings for light weighting. What I didn't mention is that there's also a concern about stray currents, electrical currents as well. So if you were able to kind of check in with our e-vehicle seminars and stuff here, the meetings, you'll hear a lot of talks from the fluid providers around electrical current, either insulation or conductivity, intentional conductivity. So you got some significant power electronics right up against this lubricated mechanical unit versus, the rear end axle of a truck, a pickup truck, where it's just mechanical linkages all the way to the wheels. So I won't spend too much time on this looking at the time, but you can have these input shafts. So you have your electric motor spinning an input at pretty high speed that is connected by gear to this intermediate shaft and then to an output shaft with a differential in it. And then the bearing selection usually ranges from ball bearing for high speed through tapered bearing for more load and mixed loading conditions of thrust and radial load. So the challenges are real. You're moving down the viscosity chart in general. You're at high speeds and bearings. You're concerned about cage damage, usually thermal runaway if you have some loss of lube or damage. NVH, so noise, vibration, and harshness. You don't want to, in a quiet electric vehicle, you don't want bearings rattling around and creating vibration and noise. And then roller skewing and so on can matter as well. So you can generate damage to the roller ends, to the cage, if things aren't dealt with on the lubrication side. What we've been able to show is that you can use in some of these positions tapered bearings. We call them EPDFEs. This is a bit commercial, but it just means a small tapered roller bearing so I could use this little guy in place of this big ball bearing. Again, because I have line contacts for my loads versus point contacts there. And when you're doing bearing life predictions, that matters. The concern then, as I've said earlier, is that do I have too much power loss due to friction in this guy versus that? And we're able to show, some cases where they're pretty comparable. Whenever you're doing torque predictions and bearings, it's always very condition specific. So there's no just single answer there. But we're working with e-axle folks, and you'll see some tapered bearings in those going forward. Just a little more of a deep dive then into power loss and bearing. So if you think about a rolling element bearing, power loss is torque times speed. A tapered bearing is an interesting example of talking about friction. You have a lot of different contact points. So you have the roller contacting the outer ring, the inner ring, this cross section again. You have the roller touching the cage in a couple places. You have the cage touching a ring usually. You have the roller end in contact with this constraining flange on the inner ring or cone. And if you break down the physics of all of this power loss, you have elastic hysteresis, you have full film lube, mixed film, boundary film, and then drag and churning bulk shear. The contributions, I mean, the majority of the power loss in a rolling bearing has nothing to do with the sliding contact. So we're not all that worried normally about the roller touching the cage, even though it's just sliding. We're not even that concerned about the rolling element touching the rib or the flange compared to the roller rolling on the raceway. So if you think about creating a hydrodynamic wedge, you're plowing through lubricant and then pressurizing that lubricant through that wedge between the roller and the raceway. And all that pressure and energy going into that creates frictional losses. So the majority of your frictional losses in a tapered bearing have nothing to do with the sliding contacts. It has everything to do with just the line contact between the roller body and the raceways. So then you get into your standard Strybeck workup where if I can have good film separation between my roller and my raceway, that's great. I can reduce overall friction, but lubricant shear losses can be significant. So it's still mechanical work on that fluid to compress it, to pressurize it. And so there is some energy loss there as well. You get into boundary friction at the rib roller end contacts and so on, but again, they tend to be in aggregate less of an energy loss than just the roller raceway contacts. Mixed mode friction is an area that's super critical for electric vehicles in particular, because now I'm using lower viscosity lubricants, and so the contacting asperities play a significant role in the amount of friction that I'm generating in my contacts. There are numerical, statistical ways to calculate this. This is a bit of a busy slide, but we have ways that we can predict mixed mode friction in our torque models. And then the last piece of this is the lubricant itself, or the fluid itself. So the majority of the EHL models that are out there, the elastohydrodynamic lube models for bearings and gears, high pressure contacts in general, are not taking into account in any real measurable or quantitative way pressure viscosity behavior. Now you do have usually a pressure viscosity coefficient, which is usually like alpha, or they call it PVC. Um, that's usually approximated for most calculations. When you start to design bearings and lube systems for very specific, high performance, high efficiency type applications, you really need to measure the pressure viscosity behavior over a range of temperatures, pressures, and then you also need to measure the viscosity influence of shear on the system. So most of the kind of earliest models didn't have high shear behavior modeled in there as well. So what we do is we measure viscosity at high pressure and temperature, allows us to get accurate pressure viscosity coefficients and models. We then have a high shear viscometer, which allows us to impose high shear on the lube and then measure viscosity. We measure limiting shear stresses, and then combine all these three things to create lube rheology models that allow us to integrate shear stress over EHL in these roller raceway contacts. So there's a lot of behind the scenes stuff that we're still working on and developing. I will say the aerospace world has been most aggressive in employing these types of techniques, but still a lot of opportunity there. And when you do that, when you use these types of backgrounds and models, and I won't get into this, you can really narrow your prediction of bearing torque, or torque being the power loss, the amount of torque that's lost or required to turn the bearing. So we have some other publications on this. We could follow up later if you'd like, but we're really trying to push the state of the art in the fluid mechanics piece of this. And then coatings, you get into, there's all kinds of thin films that matter. Natural oxides will form. You have reaction tribofilms. You have chemical conversion coatings. This engineered thin film coatings is where we intentionally will deposit like a diamond-like carbon or a amorphous hydrocarbon with tungsten in it. These are in most wind turbines you see in the world now. In particular, the tungsten DLCs that have this nanostructured thin film layer. They're only 1 to 2 microns thick, and they're nanocomposite engineered dispersed carbide type structures. So creates some lubrication opportunities as well, and allows you to um, get in and improve micropitting and smearing resistance, for example. Okay, so just on the bearing side now, and I don't have as much material on the industrial motion, but just to wrap up the bearings, battery electric vehicles, exciting new development area for the world of bearings and lubricants. Increased axle weight ratings, lower centers of gravity, e-axles with high speeds, very low viscosity lubricants. These are all really driving a lot of decision making, kind of basic decision making around bearing selection and design. We're trying to improve our ability to do that with modern rheological methods and so on, and then application of coatings where appropriate as well. So, pictures of e-vehicles, certainly main shaft turbine engine bearings and wind turbines, some of the hot R&D areas in the bearing world right now. Going on to industrial motion here for the next 5 or 10 minutes or so. Robotic material handling, we call it lights out or dim lights manufacturing. So I could just turn the lights off in the factory and it'll keep pumping out production without people. Lean flow processes, material utilization, waste reduction. These are all things that are driving decision making and design of manufacturing automation solutions. Just in this brief little talk, just a few words on automated lubrication systems for manufacturing equipment, and then robotic motion control components. You think often about rolling element bearings and gee, I gotta oil or grease those. Same with gear drives. You got some little widgets here in these really high precision gear drives that are requiring lubrication as well, although they're easy to forget about because they're often little package sealed units. So I want to spend a minute or so on that as well. You'll find automated lubrication systems everywhere in machinery. In this, the pump automatically applies lubricants to equipment bearings. It eliminates labor, improves reliability versus fighting with the grease guns and so on, like we were talking about earlier. The other thing is that an advantage in this is that you're you're injecting the lubricant while the bearing is being used in a lot of cases. So it actually entrains the grease into the bearing better than shutting everything off cold, squirting it in, and then starting it up all at once. So you kind of meter in the lubricant as you go, and you can kind of keep closer to that optimum level as the rotating bearing actually helps lubricate itself versus, again, kind of a cold greasing or something. Um, so you can get to increased efficiency, higher productivity, and decreased maintenance overall. Ideally, you want your bearings to run without any issues, and this takes a lot of the human error out of it. However, 80% of all greasing points in the world are still manual. So there's still a need for STLE to work with people that do this work. Um, we're just saying that there are specific cases and end uses where you can automate some of that and turn your lubricant experts on to other more challenging issues than having to do the grunt work directly. Um, these systems can be configurable to application needs, from 000 to NLGI2, across all kinds of ranges of temperatures and pressures and flow rates. Multiple point lubes, single point lubes. There's a lot of variation there. And so the systems are often designed to the application directly rather than being an off the shelf kind of a thing. Um, Industrial robotics. So we acquired a company called Cone Drive that makes strain wave gearing or harmonic gear units, usually in lighter duties, pretty significant reduction ratios. Um, Acquired a company called Spinea that does cycloidal reduction gearing, usually heavier joints, more load bearing, and then robotic transfer unit linear bearings and linear motion bearings are another component of this as well. In strain wave gear drives, you have a gear drive module. It's kind of like a spirograph if you think about like the toy, um, where you use a wave generator with an elliptical geometry that as it rotates around this flexible spline, engages one tooth over per turn. And so that's how you can get pretty big output ratio changes from 160 to 1, for example. You'd have like 160 teeth um, there and so on. So it's a very mechanically interesting thing, and it's a very compact unit as well. If you have these and you come across them, they do require special lubrication. Um, the factory will lubricate them in a Class 8 clean room or better. The components are all match sets, so you don't want to pull the thing apart into 1,000 pieces and then try to put it back together because you're not going to set it up the right way. So the advice is to look to the component manufacturer for the lubricant requirements. For the ones that we produce, we have only an approved grease that we use. We don't encourage greasing with whatever you have in the shop. And then we ask that you follow our processes and procedures pretty closely on those. The cycloidal reduction, so the heavier duty ones are not much different in terms of complexity. You have a lot of little bits and pieces and rollers and teeth and rotating components. It also uses eccentricity on a rotating shaft to create a cycloidal movement and kind of meters the output around. You can get up to pretty high gear ratios with these as well. Very high precision, zero backlash, all kind of ground finished components and little bits and pieces in there. And so, yeah, more than 300 moving parts in that example. These can be lubricated with grease or oil, though. They're a little less picky than the harmonic gear units. This is like a horizontal. You can have an oil level, gives you an oil 70 to 80% of the free space. Vertical installation has, a similar kind of guidance. Um, Manufacturer guidelines are key, of course. But again, you don't want to mix lubes and get too crazy with these things either. And then we always forget about linear motion. Like, how often do you grease the bearings in your desk drawer sliders. But okay, scale that up to industrial robotics. Now you got big, heavy, expensive equipment. You want to grease those sliders and so on. So everything from these, autonomous vehicles to vertical storage units to stacker cranes, conveyors, shuttles, they all have these kind of linear units. And if you get in and look at it, you have a bit of a diversity in the types of lubes you would use. Full synthetic oil for certain compact roller wiper heads. You have these kind of circulating ball guides that use fluid, you know, NLGI 00 or whatever grease. This is just a more standard lithium NLGI 3, with a higher viscosity for telescopic slides. Rollers have different requirements as well. So again, this is not to say, this is the way you always do it, but don't forget about this stuff. It needs lubed as well. And I'll wrap it up with that. So, you got some pretty interesting mechanical designs in some of these compact drives and robotics and so on. They need to be lubed, but usually not with just one lube. You have different lubes and different lube requirements for these sealed units. Linear motion bearings require attention as well. And then lastly, yeah, if you have a place that's hard to get to or unsafe to get to, or you need to take advantage of some of the benefits of the auto lube systems, there are a lot of companies that can do that and can work with you on that as well. Okay, so that's the end of the technical stuff. I guess we could take questions if there are any.
Yeah, thank you very much. Let me see in chat. I have a question that Ken asked. He says, "Is there a particular grease thickener or base oil that works better for roller bearings?"
I don't think there's just one. Each of the kind of standard grease types that we use for roller bearings has their pros and cons, of course. Um, but we commonly, we'll spec well, we don't, oftentimes we don't spec it, but if asked for advice, we point to kind of the standard lithium complexes. But we've done research with polyurea greases, with calcium sulfonates, some of just the lithium soaps. We've even experimented with other non-lithium soaps and so on. We're seeing more and more semi-fluid kind of grease applications, and so our sealing requirements have gone up, just as a general statement. When I started 20 some years ago, it was mostly all NLGI 2 and 3 kind of stuff, and we're seeing a lot more semi-fluid grease grades now. And I think some of that has to do with just trying to take friction out and so on. But yeah, that's what I can say
Okay.
about that.
Okay,
Yeah.
thanks. There is another question that says, for a sealed system, what type of grease is used for lifetime application without any refill or replenishment?
For a sealed system,
Yes.
any of those greases I just mentioned can be. Um, if you think about wheel end bearings, like we were talking about with battery electric vehicles, there are those are mostly sealed for life. So when's the last time you've changed the wheel end grease in your pickup truck at home? Never. And so what we do is we'll work with the OEMs to select and validate, qualify certain greases that we then factory fill, and they're sealed for life. And
Okay.
again, these are not fancy. These can just be, lithium complex from companies you've heard of that have the right antioxidants and the performance additives in there. Now, we do a lot of seal qualification, so we're constantly testing these packaged units and flooding them with all kinds of contaminants and water and sealing them up and testing them for certain long times and then pulling them apart and looking to see if there's any loss of grease or so on. But that's all pretty much figured out experimentally today and has been for decades.
Okay. And there is a question that probably you have heard a lot. There is a rule of thumb about the viscosity of the base oil of the grease based on the something that we call it the speed factor, the dimension and rotational speed of the bearing. Can you comment on it? Is it a good tool to evaluate the viscosity that we need for the grease, or there are better ways to do it?
Yeah, most of the grease selection. So when we calculate bearing life or estimate bearing life based on our models, and we know it's going to be a grease lubricated situation, we'll use the base oil viscosity of the grease for those calculations.
Mm.
So we're doing just the normal EHL kind of calculations for film thickness, and then relating that to our life models, for example. Um, so yeah, the base oil, the grease is usually what you use. The viscosity of the base oil is what you use to do your life predictions for your bearing. I will say that we are evolving more though to looking at the thickener as well, especially as you go to more semi-fluid type greases where the thickener is actually entrained into the contact, especially at first, and then so that can actually have some beneficial effect there as well. But yeah,
Okay,
that's
thanks.
that's the
So
way we look at it. Yep.
we have another question in the chat. Says electric vehicles appear to have quicker acceleration versus gas engine vehicles. Does this affect bearing selection?
Yeah, it does. I mentioned real briefly going through there, you have to make sure that the axle attaches to the bearing with a heavier duty spline than maybe you would have in an internal combustion engine. That's for your takeoff torque, so you don't just strip the spline right away. You do have, your grease has to accommodate that as well. So your temperature curves and your load curves and everything are different with that kind of takeoff, higher takeoff, higher torque takeoff.
Okay, so the next question is for bearing life for gears for grease lubricated bearings. Why is not the apparent viscosity used instead of just probably the basal
Base
viscosity? And
oil.
how do you account for some greases that shear down?
Yeah, so the apparent viscosity is great initially, but when you run these curves, you can see that you kind of start with a high, kind of a high apparent viscosity, and then it eventually with operation will thin down to the base oil, just due to the bleed and there can be some shear degradation to the thickener if it's entrained through that high pressure contact as well. So it's more conservative to design your bearings based on the base oil alone, and if you get some higher apparent viscosity, then it's just bonus. So we're trying to design to something that will give us a little safety built in, and that's the way that's done. Now there are some models, where people will say, okay, I'm going to be more precise. I'm using a semi-fluid. I'm going to have more entrainment. My curve of that apparent viscosity lowering to the base isn't as steep, maybe, as some of the earlier designs. But um, yeah, there are different ways of looking at these things, and we'll work with our customers on it in general.
Okay, thanks. There is a question that says, how do DGBB, I think that's deep groove ball
Deep
bearing,
groove ball bearing, yeah.
compared to TRB, taper roller bearing, in respect to NVH characteristics in BEVs?
Yeah, so that's an interesting question. So you can get balls to be really round. And so, when you think about NVH and vibration signatures and so on, it has a lot to do with the manufacturing processes to create the roundness of the raceways and the rolling elements themselves. So when you get into when you look at ball bearings, balls are easy to make round because you usually use lapping and there's geometrical control over that. Now you still need to understand the size and have the size complements right and everything. But ball bearings can be quieter in general than rolling bearings, and not just tapered, but cylindrical and spherical as well, because the ability to achieve that same roundness on a tapered kind of body is not as easy as just parallel plate lapping, for example. And so you're usually looking at higher precision classes. We think about undulations per revolution, and both the raceways and the rolling elements, the rollers themselves. So you can engineer out NVH in roller bearings, but ball bearings can be easier to work with, just based on the manufacturing differences. So if you're
Okay.
going to a roller bearing in some of these high speed things, you get load advantages, but you got to worry about NVH and you got to worry about your power losses, of course, your friction.
Okay,
So it's always
great.
trade-offs. Yeah.
Great. Any other questions? I don't have any other question in the chat. If somebody else has a question, they can unmute and ask, or you can type in the chat. One question for myself. For the EP properties of the grease, what kind of tests you do at Timken facility?
We do not do the Timken OK load,
Oh,
weirdly enough. We can. So the Timken test, people always talk about the Timken test. That was way before my time, but yeah, that we sold that off decades ago. Even though our name's still on it, it's funny. No, we look at a variety of things. I mean, of course, the real proof is in the full bearing testing,
mm,
where we get the lubricants up to application temperatures, and we put reasonable loads, if not aggressive loads on the products, on the bearings. And then you run them, and you can compare through Weibull statistics kind of the life performance with and without different additive formulations. Um, there are things we can do at the tribometer scale. We can do ring on block, although that's sliding. We prefer to do rolling sliding contacts. So we'll use a ball on disc or a roller on roller that we run. And we can carefully control the temperatures of those experiments. And then we can cut up the samples and look at the tribofilms that form and microscopes and do different things like that. So it's a combination of all those things, but it's always the final proof's always in the life testing, or an application test that mimics what's going on in the field.
mm, okay. Thank you.
Yeah.
So I don't have any other questions in the chat. It's
Okay.
10:58. Anything else that you want to add, Ryan, before we close the session?
No, I don't think so. Just I'm so glad to see so many of the Toronto members on here. We're all ears. We want STLE to be the go-to place. We are. I keep using the word community because we are one. We're all sharing our interest and our, in some cases, love for the field we work in, and we should lift each other up as well as we can. So that's why we're trying to put the tools in place to allow us all to associate with each other and get business done, and learn a little something along the way. So appreciate your participation, and I hope to run into you in the future.
Well, thank you very much, Ryan. Thanks everybody
You,
for joining us. This webinar was recorded. I will upload it into the Toronto STLE YouTube channel and the website. Thank you very much and have a great day. Bye now.
everybody.
Thanks, guys. Thank you. Bye.